Okay, today's lesson is 3-2, Solving Systems Algebraically. You may notice that we skipped over 3-1. We'll talk about that in a minute, but 3-1 was solving systems, graphing, or with tables. So in this chapter, we're going to talk about a linear system of equations, which means we're going to have more than one line, and we're going to try and find out where those two lines cross. Where they cross, where they intersect, is called the solution to that system of equations. Since a linear system has two variables, we're going to need two equations to be able to solve it. So here we have a little bit of what was in chapter 3-1, where we'd have to graph to see where they cross or make a table to see where they cross. And back when we were in pre-algebra and maybe even a little bit of algebra 1, it was okay to graph and say, oh, it crosses at this point. But the problem is to tell where two lines cross in a graph, they have to cross at an intersection on the grid paper, or we're just guessing where they cross. And even if they it looked like they crossed at a corner, well, is that because it just looked that way, or maybe we didn't have that straight of an edge, or something along those lines. So graphing doesn't really work, especially here in Algebra 2, because sometimes our answers will be fractions or decimals, and there's no way to tell what those are by graphing. And the problem that we have with making a table of points is that, again, if our domain, if our x value was 1.73, well, we're not going to put 1.73 into a table and guess that there, because there's an infinite number of domain values that we can pick. So these two ways are not viable in Algebra 2. So here are the different outcomes that we could have when we have two equations of a linear function. We could have intersecting lines where they cross at one point. I don't really care if you know the word consistent or independent. I just want you to know that if they intersect, they'll have one solution. Let's come over here to the far right. If they are parallel, they will have no solution. And here you'll notice that the line is purple, where the other two graphs were blue and red. That's because when you put blue on top of red, it becomes purple. In this one over here, the two equations were actually equations that graphed out the same line. So it's like the same line on top of itself. And we don't say all real numbers here because now we're in a coordinate plane where we're talking about points in ordered pairs. So we say infinitely many solutions because we can't list them all out, but to say all real numbers isn't quite right. So here are my three possible outcomes: one solution, no solutions, or way too many solutions to list. When given a system of linear functions, we should be able to tell which of those three things that we just looked at they work. Is there going to be one solution? Is there going to be no solutions? Or are they going to have infinitely many solutions? And I say that the easiest way to do this is to put both equations into y equals mx plus b form, and then look at the slopes. Because if they're the same slope, then it's going to be parallel or maybe the same line. If they're different slopes, it's definitely intersecting. So once we get the same slope on the two lines, we got to go, okay, do they have the same y-intercept? If they have the same y-intercept, well, think about that. Same slope, same intercept, same line. So let's go look at these two problems here. We put them into y equals mx plus b by moving some stuff around, and we notice that they have the same slope, but they have different y-intercepts, which means if we were to graph these two lines, they would be parallel. And since they're parallel, we would say that there is no solution. If that slope was anything else other than 1/2, we would say that there is one solution, that these two lines intersect. So if we can't solve a system of equations by graphing because we can't be precise enough, or we can't use a table because there's an infinite number of domain choices to use, what can we do to solve? So here are the two methods that we have. Hopefully you remember these from a couple years ago. We have the substitution method and the elimination method. Now, I don't like to call the elimination method. I like to call it the addition method because I always want to put a plus sign in there when I do it. So I'll show you that when we get there. So here let's do one by substitution. And I will tell you that the way this is set up, I probably wouldn't do substitution unless I was asked to do substitution. But any type of system of equations for linear functions, we could do substitution. The first key is to get one of the variables by themselves. You have to isolate one of those variables. And I have 4 to choose from. Of those 4, this y right here is probably the easiest one to get by itself because all I got to do is move that 2x over. But I could get that y by itself or this x here. Doesn't matter. So substitution is taking something out and putting something in that's equal to it. And if you remember from earlier videos, I'm a big fan of parentheses. So in substitution, when you take out a variable, you take out one term, you can only put in one term. So when I get this y by itself over here, you'll see that I moved the 2x over. If I didn't put those parentheses around it, that would be 2 terms. And I can't put 2 terms in place for 1 term. So I put parentheses around that, and now it's 1 term, and I can replace the y in the other equation with that 1 term. And it looks like this. See the 4y, well, the 4 stays and the y becomes that parentheses that we just made. And now all I have are x's, and since I have x's, I can go ahead and solve for x. And we get 5.6. By the way, I really don't like that answer. I would rather see you do it like this. Negative 5x plus 40 equals 12. Subtract the 40 from both sides and get negative 28. Divide by negative 5. This is a much better answer for an Algebra 2 honors student, 28 over 5, which really is 5.6. But if we get used to writing in decimals, we're always going to try and put something into a decimal. And if you have to round a fraction, you're going to lose points on my test, because if I don't ask you to round, I don't want you to round. So I would much rather see you use the fraction. So I'm going to go ahead and substitute that 28.5 into this top equation. Now, I know that we should put it into the bottom equation because it is much easier, but there's something I want to show you when we do it this way. So hold on just a second, we're going to do it. All right, so I have this fairly worked out here. I substituted in the 28/5 for the x. Then I multiplied the numerator. 3 times 28 got 84. The denominator is 1 times 5 and got 5. You'll see that I turned the 12 into 60 over 5 because they're the same number, and now I can put the 84/5 with the 60/5, and I get negative 24/5. I did all of this, I did this equation because I wanted to get to this point right here, because this is where I want you to understand something. I want to divide both sides by 4, right? I have to get the y by itself, so I divide both sides by 4. Well, I have a lot of students that will do this and give me that for an answer. That's called a complex fraction. We cannot have complex fractions in Algebra 2. That is one of the things that we have to stay away from. So let's get rid of that. Let's read what this right side says. It says negative 24 divided by 5. Well, I want to divide by 4. I already have a divided by symbol, so I don't need a second divided by. The key thing here is to make sure that your denominator is 1 term and what you're dividing by is 1 term. If they're both 1 term, then you can take that 4 and just put it in the denominator, and you divided both sides by 4. What you're really doing is multiplying by 1/4. You're multiplying by the reciprocal. You're not dividing by 4. So really it's negative 24 over 5 times 1 over 4, and you just multiply your numerators and denominators. And then I will reduce that guy and make that a 6 up top, and I get y equals negative 6/5. Now I haven't given the point yet because I have to put it into an ordered pair. If you leave it like this and like this, these are 2 lines. 2 lines that do not cross at 2 lines. 2 lines cross at a point, so make sure that you put it into ordered pair form, and this is what the answer should look like right here. Now, I'm okay with this answer that they gave over here because those decimals ended, But if you're using your calculator and it fills up the screen on your calculator and you're going, I'm only going to put you're rounding. I didn't ask to round, so don't do that. Okay, so substitution is not my favorite method. I usually only use substitution method if it starts out with one of the variables already by itself. The elimination method, which I call the addition method, is what I like to do. And the first thing you do is you line up your two equations. So your x's line up, your plus signs and minus signs line up, your y's line up, your equal signs line up, and your numbers on the right-hand side line up. And then without using a pencil, you add these two lines together. Hopefully one of the variables will be eliminated, it will disappear, makes a 0. If it does, then pick up your pencil and solve. So in this case, I see that it does, the x's will disappear. So I'm going to go ahead and add these two things together. I would like to see a plus sign out here, right? And you get a y. So you got 5y equals 25 divided by, so we solve for y. That's half of your answer. What you might want to do is when you see this question, before you even do anything, go to where you're going to write down your answer, put an ordered pair, and then when you get one of the things, put it where it's supposed to go. Because right now, y equals 5, that's just a line. That's not what we want. So now we go to one of the two equations from the original, and we substitute in with that answer, solve for x, and we get the other half of our answer. Now on a test, if we have time at the end, we should always go back and check these answers and make sure that we have it right. But we did the right math there, so we're good here. Here's another example that we have going on. First thing I want to do is I'm going to make sure my x's are lined up, my y's are lined up, the equals are lined up, the numbers are lined up. I put my pencil down and I add these two things together and I get 5x plus 12y equals -1. Well, nothing disappeared. I need an x or a y to disappear. So I don't pick up my pencil and write that down because that doesn't do any good. So what kind of numbers, when I add them together, will disappear? Well, they have to be the same number, but different signs. So you get to pick which variable you want to make disappear. Which variable do we want to eliminate? If I use the x's, what number could I turn a 2 and a 3 into? Well, I could turn those into 6's. If I wanted to get rid of the y's, what could I turn a 7 and a 5 into? Well, I could turn those into 35's. But one of them has to be positive and one of them has to be negative. So here we decided to get rid of the x's. So I multiplied the top, every single term, not both sides, every single term gets multiplied by 3, and the bottom, every single term got multiplied by -2. Could I have multiplied the top by -3 and the bottom by +2? 100% could have done that. So now when we add these two guys together, the x's get eliminated. I can solve for y, and remember, I should have gone to where I'm going to write my answer, put an ordered pair, and now I can put 2 right there. Go to one of the original equations. We'll go back to one of these two guys, pick one, put the 2 in, solve, 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 and you got your other answer. And if we had time on the end of the test, we would go through and check that answer. You may not get the right answer, but at least you'll know that it's wrong, and you'll say, well, I couldn't have gotten 100 on that test because I definitely got number 13 wrong. Hopefully you won't do that. And last but not least, we have some problems where, let's just go ahead and do them. So the first thing I notice is it's not set up the way I want it. I want my x's first, my y's second, and then my equals, and then my numbers. So I'm going to move the 3x over, making it -3x plus y equals 1, -12x plus 4y equals 3. Well, I can't add those together, so I'm going to have to turn these. I can turn the x's into, both of them into 12s. So I'm going to multiply by -4 by all of these guys, because they need to be opposite signs. And I get 12x minus 4y equals -4. And I get -12x plus 4y equals 3. And I add these two guys together. The x's disappeared and the y's disappeared, which leaves a 0 and -1. We've had this happen before where my variables disappeared, and we would read what's left. And if it was a true statement, we would say all real numbers. If it was a false statement, we'd say no solution. We do pretty much the same thing here. If it's a false statement, we say no solution. These must have been parallel. If it's a true statement, we say infinite solutions because they're the same line. So on this one, 0 equals -1. Well, obviously that's not true. So we say no solution because they're parallel. You don't have to put the parallel part. And on this one, if we worked it all out, they would actually be it would be a true statement, and we would say infinite solutions. Okay?